Welcome to the deep dive. Today we're digging into something really interesting in self-supervised learning. Joint Embedding Predictive Architectures, or JEPs. The
Hmm.
models like Data V2 built on this. They were kind of hailed for like cutting ties with complex generative stuff by avoiding input reconstruction.
Exactly. And our mission today is to figure out why these GPUs seem to really encourage their outputs, their embeddings to look Gaussian, and also how this seemingly simple part, the anti-collapse term, is actually doing something quite sophisticated underneath. It's secretly performing density estimation.
Yeah, that's the real kicker, isn't it? We praise GPs for being streamlined, non-generative. But it turns out they were hiding this capability all along, basically doing non-parametric density estimation of the data they were trained on. Wild.
Okay, so let's back up a bit. Think about the goal for the representation itself. In SSL, a big motivation is maximizing, let's say, the informational diversity of what the model learns. We call that the embedding path, like Scott. And to get that maximum diversity, you often want to push the distribution towards Gaussian.
Why Gaussian, specifically?
Well, because the Gaussian distribution is the one with the maximum possible differential entropy, given certain constraints on the covariance. It's basically the most spread out or, random shape the information can take, given those limits.
Okay, so pushing towards Gaussian is really about maximizing how distinct the learned representations are, making sure they're not all clumped together.
Yeah.
And that brings us to the anti-collapse term you mentioned. That's key here, right?
Precisely. GPIs fundamentally have these two main objectives.
Right.
One is the prediction task in the latent space, and the second is that crucial anti-collapse term. It's kind of the safety net. It's the regularization part that stops the whole network from just learning to output one single, trivial, useless thing for every input, collapsing.
Right, avoiding that collapse. And what's really fascinating and what the research uncovered is this deep theoretical link between that safety net and, well, generative modeling concepts.
Yes. The core theoretical finding, the math basically shows that pushing this embedding in theta towards maximum entropy, essentially making it Gaussian, only works if the deep network is somehow forced to implicitly learn the underlying density of the original data. And this holds true regardless of the specific dataset or the exact GPA architecture being used. It's quite fundamental.
Wait, hold on a sec. If it's learning the data density, P.S. when? I thought the whole appeal of GPAs was that they skipped things like explicit input reconstruction, which was the hallmark of older generative models like VAEs or genes. How is learning the density not generative modeling, in a sense? Are they really that different?
That's a really good question, and it's about the how. JPLs aren't explicitly trying to generate data samples based on the density. Instead, they're sort of internalizing the structure of the data density because it's necessary information to achieve that goal of maximal entropy in the latent space. So if you ask, can you specify the density of the embedding phi SS1 without the network 5 hours learning anything about the input density? The answer turns out to be a pretty definitive no.
Okay. So it's an implicit learning process driven by the entropy goal. But if JEPAs do implicitly know this density, how do we, actually see it or use it? We need some way to extract it.
Exactly, and that's where the practical tool comes in, the JEPA-SCORE. The JEPA-SCORE is essentially the method developed to pull out that implicitly learned input density px of echoes. And importantly, it's efficient. You can compute it directly in closed form using the model's Jacobian matrix.
The Jacobian. So that measures how the output embedding changes when you make tiny tweaks to the input $6.
Precisely. Think of it as measuring the sensitivity. How much does the output wiggle when you nudge the input?
And that sensitivity score tells you how likely the model thinks that input is based on its training.
That's the core idea. It gives you a measure of how comfortable the model is with that specific data point, which acts as a proxy for its likelihood under the learned distribution.
Which immediately suggests applications like outlier detection.
Absolutely. And the empirical results they showed were quite striking. They took a JEPA trained on, say, ImageNet. Then they fed it samples from datasets that had never seen during pre-training, things like images of galaxies or MNIST digits. Those out-of-distribution samples consistently got dramatically lower JEPA scores compared to the ImageNet data it was trained on. It clearly flags them as different.
So it's a good detector for stuff the model hasn't really learned about. That makes sense. And it goes beyond just inverse out-of-distribution, right? It gets into the quality or semantics within the training data, too, like the bird example.
Yeah, that was a great illustration. They looked within ImageNet, specifically at bird classes, and they found that the JEPA consistently gave higher JEPA scores to images depicting birds in flight, whereas images of birds just, sitting on a branch or on the ground tended to get lower scores.
Wow. So the score isn't just about likelihood. It's capturing some kind of semantic prototypicality that the model learned, what it considers a good example of a bird, maybe.
It seems that way. It suggests the score is linked directly to the model's internal representation of what constitutes a high-quality, perhaps more informative or representative sample for that concept it learned.
This really changes how we might think about these models.
It's quite profound, really. We thought of JEPA days primarily as representation learners focused on getting good features. But it turns out they're also functioning as non-parametric density estimators, hiding this complex capability inside that relatively simple-looking anti-collapse regularization.
So wrapping up, the big takeaway is this unexpected connection. JEPAs learn representations, yes, but to do that well, pushing towards Gaussian entropy, they must implicitly learn the data's density, which leads to this final thought for you, the listener. If the JEPA-SCORE gives us this window into the learned data distribution, allowing us to spot outliers and even assess semantic quality, how might this change how we select, curate, and even evaluate the massive data sets used to train future foundation models, things like the next Dino or MetaCLIP? Could this give us a much sharper tool for building better training sets? Something to think about.